Rejoice, Sam.
We have figured it out. My book has an error. It really does, I promise. What page is that?
I bet it's like the 4th printing. Mine is the 6th.
Alright, I am making a note. Here it is. Okay, step one, misprint, that I know. Okay, we're good. So we actually did find the index of refraction of water successfully. Yes. Alright, so now what we're going to do is talk about everything else I know, which isn't much, about lenses and mirrors and how to use them in the lab. But I'm not going to spill that water all over the world. Okay, so let's grab a sheet of notes for me. Alright, so when you have, we'll talk about mirrors first. We talked about mirrors first last week, right? Does anyone see an eraser? Oh, good, thanks. Okay, so concave mirrors. If you happen to have colored pencils or something, please take your test with colored lines. It makes it a lot easier. Okay, for a concave mirror, I'm going to write what I know on the board, and then you can kind of look at it as you play around with them. There are some equations that work for lenses and for mirrors. The inverse of the focus is equal to the inverse of the image distance plus the inverse of the object distance. That's not a 0, it's an O, because we don't like undefined numbers, right? So what that effectively looks like is if you take a lens or a mirror or whatever, and you put your image or your object here and the image forms clearly here, then you can calculate the focal length by adding the inverse of this distance to the inverse of this distance. So you solve for 1 over f, but you really want to find actual f to find the focal length. There's another way to find the focal length for a mirror. What is it? Let's see. So, right at, okay, so if you take a mirror and you look in a concave mirror, let me find one. Hopefully that it's in the right box. If you look in a concave mirror, what are you going to see? That is a lens.
That's rather unfortunate. You'll
it's
see
in the mirror box too.
A reflection
lens.
of whatever it was.
Ah, okay. So this is a magnifying mirror, so it is convex. Concave. Okay. So a concave mirror, if I look in it, I see a very magnified image, right? If I continue to move it until I get right at the focal length, my image like disappears or is very, very, very blurry due to spherical aberration. Yes, everyone's going to try. And then when I get past the focal length, my image should invert. My arm's not long enough for this. But like if I look at somebody else, you guys are probably far enough away. If I can find somebody. Well, maybe you're upright still. Maybe you're not far enough away. The one way to find the focal length, though, is to measure the distance of a really far away image. That, like, say the clock. If I find the clock with this mirror, which is difficult since it's so small. Well, that's something you're going to do. You're going to measure, you're going to find the clock, find where the clock is really clear, and then measure the distance with like 8 yardsticks or something. And then you can figure out the focal length. Let's see. So here's what I know about a concave mirror. Alright, so if the object is closer than the focal length, it is upright. If it is clear, magnified, inverted, you are just past the focal length. When you pass the radius of curvature, you get a real image. So we should be able to create a real image if that can in fact happen. It should be reduced and inverted. Anything else interesting here? A convex mirror is always going to produce a virtual upright reduced image. That's what rear view mirrors are. You'll never get an inverted mirror or an inverted image in your rear view mirror because that would be really dangerous when you're driving along.
Is there any mirrors, rear view mirrors that you could make where, like, because it says objects in mirror
Are closer than they appear.
That's why, because a convex mirror always gives you a virtual upright and slightly reduced image.
Right.
You know
So
what I
a slightly
noticed?
reduced image might appear closer to you.
I think it's only the passenger side that does that. Because it looks bigger in the driver's side.
Yeah.
And it doesn't have those words.
Maybe it's just a plain mirror.
So, like the driver's side is plain, but the passenger side makes it look smaller.
Okay, so.
And you made me laugh, and it lost the image. I had it all the way up here, looking at the clock, and you made me laugh, and it shook, and I can't find it.
All right, so watch this. Let's.
I don't remember. You
Actually,
said
I'm
something.
gonna have you guys do it because I can aim Sam at you. Can Sam see? All right, so hold this mirror, and Nick, you look in the mirror, and I want you to draw an outline of like how big your head is, or some part of you in the mirror. Like get close to the mirror and draw an outline of like your nose or your, or, something that you can tell is a certain size, like your whole head or.
Like your eyeballs.
Yeah.
This is your head.
Now,
You keep moving.
now back up like a bunch of back
You must
up
have
a bunch
you have
and
a
see
narrow
if,
face.
see how your image changes if you move further from the mirror. Is it the same size or smaller?
Considering
or bigger?
what the shape looks like on the mirror, it looks rather funny.
Looks like a potato.
Okay, but will the same
How
amount
is
of
that
your face
shaking
still
it?
fit? Or
I
you
don't
can try
know.
again.
Try again. Get rid of it.
Wonderful.
No, you can do
My
it.
poor broken
What?
mirror.
Oh. Oh my goodness, that's so nifty.
Now we know.
Have you ever drawn on a car window with those markers?
Does it work?
It's fun.
Alright, I'm gonna do it now.
All right.
Mom.
I'll outline that.
Here, draw my hand, like the size of my hand.
Don't screw up.
Don't laugh, Josh.
You're terrible.
We need a mirror that's like glued to the wall.
Yeah, it's not moving. I'm not going.
Alright, how about
Do you have
this?
like duct tape or something? That's not bad either.
Draw it.
Just
Yes, you can get marker on me. He's taking every advantage of this getting marker on me thing.
Make one of those turkeys.
make a turkey.
You have to stick your thumb out a little further to make a turkey. Okay, now,
It still looks horrible.
like,
Whoa. Yeah, it has changed a lot.
man, that's kind of a bummer because my friend Stu told me yesterday that
Can I
the
draw my
image should
phone?
stay the same exact size no matter where you went, but that totally doesn't happen.
Whoops.
Okay, so I'm going to more blatantly discuss a test question since that totally didn't work.
It probably won't erase off that.
So, here's the thing. If, yeah, you don't want to draw on your phone.
Yep, it
on the
works.
screen, does it?
Yeah.
Okay, so
So cool.
when you're looking at yourself in a mirror, how tall does the mirror have to be to let you see your entire image, feet to head?
Yourself?
Does
From
it have to be
waist.
the full height of you?
Yes.
Has to be shorter
It does have to be shorter than yourself. That you can still see your full image in a mirror that's shorter than yourself, but exactly how much shorter than you?
6 inches.
Nope. Okay,
That's how
so
tall you are.
here's the mirror. Here's you. Where do the light beams go?
Down. Up.
Okay, so they go from your eye, right, and then they reflect back. So how tall does the mirror have to be? There's a drawing in your book
Isn't it
that's
like,
way better than
doesn't
my
it
drawing.
depend on how far away you are?
too? Like, if you have
Not according to the book, but certainly according to the experiment we just did.
Josh, did you break this?
What? No, it won't work.
Oh, it's turned off here, I'll do it.
It has to be as tall as your eyes.
Well, but it doesn't have to be as low as your feet if it's as tall as your eyes. If it starts at your eyes, it ends where?
Oh, it has to be half the distance from. Wait, no. It has to go at an angle from your eyes down to your feet, so it has to be as far.
Wait, there are
Down
mirrors that are as
from-
tall as you and stuff, right?
This is a flat, plain old mirror. So half your height is the, I think, answer, and I think this is a real test question too.
Oh, okay.
And I'm actually going to look because I really thought that thing that Stu told me to do was going to work because he has a PhD from MIT and it totally didn't work, and I trusted him.
Sam, does that or does that not look like some modified form of hangman?
Oh no. I'm looking at. Okay. Man, there's no mirror question about that on the test.
It's not gonna work on paper.
I thought it would.
No.
What's a good kind of mirror?
Well,
Spherical
on
or
this, though.
parabolic?
Probably not. You can try it.
Parabolic.
Just do it on some.
So if y'all
Don't do it
wanted
like out
to
in the
make
middle.
really good optics for like a space telescope, you would want to use parabolic mirrors,
Why are
right?
they really so hard to make?
I don't know. I don't know
Like,
about
it's just a
This is so
parabola.
awesome.
Okay, so here's what I know about lenses that can fill a tiny fraction of my chalkboard. Okay, so if you have, different color, if you have a convex lens, you can, find the focal length 2 different ways at least. Oh, this is why the mirror thing didn't work. You can do it with the convex lens. Find an object that's very far away. And get a clear image of it.
Oh, it actually worked.
And then measure, and the lens, is focal length away from the image at that point. But the object has to be very far away. Or you can
Like a mile?
do this. And we're going to have to figure out how to build this. But if you take 2 little things like this and you put a lens in between them, a convex lens, it's going to invert the image. So when you look through the lens, when you see one sitting right on top of the other one, then you are at 2 times the focal length for both of them. So I want you guys to try to build that where you have your object and you have another object and you have a lens, and then when you see this right on top of it, when you're looking here, your eyeball is looking through the lens there, and you see that, then you're going to, that's a terrible eyeball.
Whoa, who's
And this is 2F, and this is 2F. So I want you guys to try that. With a lens, you can use a candle to find magnification.
Do we have a candle?
So you're gonna have, we've got a candle.
Yes.
Pick the normal
Can I take the
shaped-
temperature of it too, please?
Sure,
later
if you can
on.
get that thing to work. Pick the normal shaped candle for this too, because I have a weird candle and you don't want that one. Where's my thing? You
Wonder how much
want,
it's gonna be, 200,
the object
800.
distance is you. So image,
No, it's gonna be over 100. 17 million. 1,300, 5 billion.
It's gonna be 5 billion degrees.
okay. So magnification is image distance over object distance. So So we'll see if that works at all, or if we think it remotely works.
92 degrees.
If you know that your image is going to be virtual, you actually have to look through the lens to see the image.
Don't you have to look through the lens to see any image?
You can see an
Like-
image on the screen with the lens. I'll try to show you what I know here.
But like, if it's real, you would still have to look through it, right?
I
'Cause
don't know.
otherwise you
Let's
just
find
see
out.
it.
I mean, this is all let's find out. I don't know a whole lot here. Where U is a distance from object. U is object. Object graph. Object distance. These are some ideas on x-axis and image distance
It says
on y-axis. Then slope is the focal length. This I really want you guys to find for a convex lens. So here's kind of what I'm thinking is I want mirror people to play with mirrors while lens people and I fool around, or we can all stick together. Do you want to break into 2 groups and play?
no one likes them.
Or okay.
Maybe
So
like
who wants to do mirrors and who wants to do lenses
Mirrors,
first?
Mirrors. Alright, we're mirrors.
All right, here, take these mirrors.
If you
Mirrors,
shine the laser
mirrors,
pointer at a
mirrors.
mirror in the dark, you can see where the laser's coming from, like a dot, and you can see a dot where it's hitting the back of the mirror. And if you put them so the 2 dots are right on top of each other, it shines in your eye.
Okay, we don't want to shine any lasers in our eyes, seriously. But you guys are going to use the laser for mirror stuff. So here's what you're going to do with mirrors, I think. This will be your image, like the object, you know, the little arrow we draw. So you'll be able to move it around and decide if it's, you can measure, decide if it's a larger image or a smaller image. We have to actually find some mirrors though, because apparently these are all totally wrong. Wrong. Anyone see any mirrors at all?
Oh, here's this little thing.
Okay. So you can put, I
Don't
put a
put the
magnet
magnet
on
near
it
the
because I was
camera.
sticking it to stuff.
Yeah, it's really cool. You can put it on this thing and shine it at Josh.
Okay, so you guys are going to take this apparatus and tell me what you learn in the next 10 or 15 minutes.
Oh, that's cool.
Yeah, 60.
So, look, you can measure the focal length because you know, like you can see it, it'll get blurry and disappear right at the focal length.
Do they like make
Whoa, that
this
is
stuff
so
just
cool.
for
And
this
then,
lab?
yes, and then it will invert and become clear past the focal length if you can find where it is. So try to find it, take some measurements, and see what you get. There should be one more
Are
mirror.
these the lenses?
Yeah. So the other 3 of you are going to stay here, and we're going to fool with lenses, and then we'll switch. Maybe we'll have figured something out by then.
What are we doing with the candle?
Here we go. Okay, here's another mirror that's different. Lens people will have to do candle stuff. Okay, if you're going to do mirrors, go here in the back because we're going to turn out the lights in here.
Oh, they're lasers.
Oh, you're wrong. You.
Alright. One extra mirror. See what you can figure out. Write down stuff. Like take a piece of paper. Alright, Christina, come over here. And did you turn that off?
Oh.